Hello everyone. So let's see this classification, finite automata classification. You already seen this classification. We have learned the finite automata with output classification, and we have also learned the finite automata without output classification. In finite automata without output, there are three classifications. One is deterministic finite automata, then next is non-deterministic finite automata, and the last one is epsilon non-deterministic finite automata. And we also see that these three machines are equivalent in power, means their power is same, no one is superior to other. Similarly, in finite automata with output classification, we have seen that Moore machine and Mealy machine are also equivalent in power, and by using some simulation and experimentation, it is also proven that finite automata with output and finite automata without output are also equivalent in power. Means all the machines, either it is Moore machine, Mealy machine, DFA and DFA, or epsilon and DFA, all these are equivalent in power. So one important point you have to note down is all the finite automata are equivalent in power. Okay, this is very important. All the finite automata are equivalent in power. Now the next concept here is, can finite automata accept all the languages which are present in the universe, or it will not accept someone? So for this purpose, let's take an example. Let's say I have a language L, A power n, B power n, such that n is greater than or equal to 1. So in this language, what are the possible strings? The possible strings are AB, AA, BB, AAA, triple B, and so on. That means the language L is infinite language. Can you draw the transition diagram? Can you draw the finite automata transition diagram for this language? Let's check whether we will draw the transition diagram or not. Let's say I have a state A, which is initial state. If I read the input A, I will go to state capital B, and on capital B, let's say I will accept any number of A's, and then after reading input B, we will go to the state capital C, which is final state, and on capital C, I will accept any number of B's. And if from starting, if I let's say CB input alphabet, then I will reject the string. Rejecting the string means we have to go to dead state, and on dead state, accepting any number of A's or B's doesn't matter. Okay, and here also, if you see A, you will go to the dead state D. Okay, so you think that this is the final transition diagram for this language. But let's say if I examine some input string, let's say AA, BB. So starting from initial state A, if A is seeing input A, then it will go to the state capital B. Okay, and if B is seeing input A, it will go to the state capital B itself. Now B seeing input B will go to the state capital C, and C on seeing input B will go to the state capital C, and we reach the final state. That means this particular string AABB will accepted by the language L. But let's not judge here and say that this particular language is comes under the finite automata classification. Let's take one more string AAB. So starting from initial state A, if A is seeing input alphabet small a, it will go to the state capital B. B on seeing input alphabet small a will go to the state capital B itself, and B on seeing input, B on seeing input alphabet B will go to the state capital C. Here also we reach the final state, and here also we reach the final state. But if you observe, AABB is present in our language L, but AAB is not present in our language L. So this particular finite automata, this transition diagram, will accept some strings which are not present in the language itself. So from this example, I can say that the finite automata will not accept some languages. Finite automata are not able to accept some languages. Then what will happen with those languages? There are some different machines, or there are some different languages which are more powerful than finite automata, and these machines will able to accept those languages. For example, in this language, L is equal to a power n b power n such that n greater than or equal to 1 is accepted by a machine called push down automata. And what is the problem with finite automata for this language? The finite automata is not able to compare the A with respect to B. The problem with finite automata is it will not compare A against the B. And push down automata is able to compare this. So in the next video we will see the different family of languages which are used in theory of automata.